In the wake of Loki and Sylvie opening up the multiverse, your job as a pizza delivery man has changed. Your customer base has now expanded to include the inhabitants of alternate universes. And while delivering pizzas to alternate universes might sound easy enough, even for this simple man, due to the perfect pizza proportions clause made by your company, you must ensure that all pizza slices are all exactly the same shape, as depicted. And, if that still sounded too easy, each of these alternate universes is spatially warped according to some mathematical function, causing any object that's transported into that alternate universe to be transformed by that function, again, as depicted. So, you need to make sure that the transformation into this other universe preserves the angle of every pizza slice in order to ensure equal proportions. Note: the perfect pizza proportions clause only specifies that every slice is the same shape. No refunds are given for pizzas that have only changed size. Given such a relatable conundrum, one might sympathize with the despair of our pizza man. However, there is hope. But we must first delve a little deeper into the mathematics behind this problem. Okay, our situation is this. We've made a pizza with perfectly identical slices. We can tell because the angles are the same. And we apply a transformation to this pizza. So long as our pizza slices are all still the same shape as each other after the transformation, which we'll again judge by looking at the angle, then we can deliver the pizza. If the angles aren't the same, like this, then we'll just give up. There's nothing we can do. And besides, a pizza that can't be shared equally might cause an argument. Or worse yet, a multiversal war. Or worse yet, a refund. So, let's stick to the universes where the transformation preserves angles of the pizza slices. With this transformation, obviously the pizza cuts bend slightly, but if we make the pizza smaller, you can see the bend becomes less noticeable. So, in theory, as long as we send exceptionally small pizzas to this universe, no one will notice, and we should be okay. Stating our problem in a single sentence, how do we determine whether a given transformation preserves angles, so that if it does, we know we can deliver a pizza? In order to answer this problem, let's take a detour to develop two tools that will have a surprising application. The life of this fish is confined to this little corridor of water we see. And since the water of our fish's home is so shallow, the fish lives in blissful ignorance of a vertical spatial dimension. He can only think in terms of two directions, forwards and backwards. I'm sure our aquatic friend is already bored of this space, so perhaps he explores further than normal. Perhaps the fish finds a place with unusual forces. Maybe he swims under a tap and then over a hole. How might our fish understand what has happened? And given only the spatial understanding of this fish, is it possible to figure out whether you're under a tap or over a hole, when the point you're at is a source or a sink? Let's consider the world from the eyes of our fish. If we found ourselves directly under the tap, of course we would be able to feel the water falling onto us. But the fish will need a different method, since it can't comprehend vertical forces. And, as the animation strongly hints, you might decide to look at whether it's easier or harder to swim as you move through a point. For example, as the fish swims under the tap, the fish will start out struggling to swim. But once the fish is past the tap, he will then find it easier to swim. The elegance of this idea of checking whether it gets easier or harder to swim is that it still works for slopes. Take a look. Here, it would still become easier as you swam under the tap, since before the tap you have only the natural water flow going with you, and then after the tap, you have the natural water flow and the extra flow from the tap. So, even with a sloped flow, the change of that flow is still the same. Also, imagine the tap was super powerful. Now, as we swim under the tap, the change of flow is huge, and so swimming under the tap doesn't just get a little easier, it gets a lot easier. This is a bonus sensitivity we have that allows us to detect not just whether we're at a source or a sink, but effectively to determine how much water is coming from the point. You can apply this thinking to what happens when the fish swims over a hole, and together you basically have a measure of how much water is gained or drained at any point. I'm going to introduce some notation so that our precise measure also has a precise representation. Let's express this like so. These curly symbols just represent change. So the top part of this is just saying, look at the change of flow. And this bottom part is basically reminding you that you are swimming in the x direction. Right, okay, here's roughly what these symbols are telling you to do. Okay, we have our change of flow and our change of x. So what does this actually mean? Well, let's imagine this is the positive x direction. Let's imagine this one is also the positive x direction. Then, what this part is saying is, let's look at the flow here, and maybe it's small negative direction, and then the flow here is small positive direction. And so we're saying, what's the difference of this to this? Well, that's 4, obviously. So that's what this part means. This part tells you to do this calculation to get 4. And this part is just reminding you you're going in the positive x direction. So let's just say this is positive 1. So we get 4. Okay, right. Let's look at this. If we have a big negative force or flow and a big positive flow, and then we take the difference, well, that's going to be 8, and then we're still going in the positive direction, so let's do positive 1 again, and oh look, this flow is bigger than this flow, which is how it should be. Notice also, if we were moving in this direction, let's see, okay, if we were moving in this direction, then this calculation, this answer for the calculation wouldn't change, because what we would do instead is we'd go from +2 to -2, so that's -4, and if we're going in the negative x direction, then this is -1, so this still gets us 4, and obviously the same is true here. So that fits our intuition that because this is a symmetrical picture, this shouldn't have a different answer depending on which direction you move. Note that when you apply these calculations to holes, this works just fine. I'm not going to show you, you can do that yourself. I'm not going to bother. Also, note, those of you that actually know what this means, or I suppose actually, those of you that don't know what this means, you in practice never actually calculate a subtraction to get this whole thing. But that's a little bit beyond the scope of this video, so you can explore that yourself if you really want to. What we just investigated is known as divergence, sensibly. We can actually apply divergence to 2 dimensions quite easily, and without giving a detailed justification, I will just tell you that when you look at 2-dimensional divergence, you look in the x direction and in the y direction, which hopefully makes some sense. If it gets easier to swim in the x direction and in the y direction, then we know we're under a tap. If it gets harder, then we know we're over a hole. If it gets easier in one direction but harder in another, then you can imagine maybe the divergence is cancelling itself out. Mathematically capturing this intuition of two-dimensional divergence is very simple. We look at the divergence in the x direction, and then we add that to the divergence in the y direction. And this does fit with our intuition we just went through. When under a tap, both terms, you can imagine, are positive. When we're over a hole, both terms are negative. And when the divergence kind of works against itself, you can imagine how the terms start also to work against themselves. They cancel out. So our formal expression checks out with our intuition. Remember this expression, it will return. And now we can move on to our other tool. Our previous tool, divergence, essentially allowed us to see if water is flowing away from a particular point. But there's another direction of flow we can look at. Instead of checking the flow away from a point, let's consider the flow going around a point. We can consider what's known as the curl. And we can apply a similar idea of our fish tracking the change of flow while swimming to determine what the curl is at a point, but with a small modification. Let's assume that we need two different terms in our calculation again, but since we don't know what they are, we'll put question marks in as placeholders. And now, let's again look at what the fish feels as it swims in the x direction, and while there's an anti-clockwise swirl. Before the fish has passed the center of the swirl, the flow through the fish is pushing him in the negative y direction. And as the fish moves past the center of the swirl, the flow now pushes in the positive y direction. So what does that mean? It means the change of flow in the y direction as we move along x is positive. Let me say that again. Previously, with divergence, one of our components of our calculation was looking at the change of flow in the x direction as we move along x. This time, as we move in the x direction, instead of looking at the change of flow in the x direction, we are going to look at the change of flow in the y direction. And it's this that becomes a component of our curl calculation. Note, this term is positive when the curl is anti-clockwise. Okay, so what's our other term? Well, you might have been tempted to just complete the pattern and assume it's the change of flow in the x direction as you moved in the y direction. But that's actually wrong. Let's imagine. Again, we will look at an anti-clockwise swirl. The term we are considering tells us to move in the y direction and feel the change of flow in the x direction. And look, the change of flow starts positive and ends negative. So our term would actually throw a negative number at us, which if we plugged into here to find our curl, would cancel out our other term and give us 0. See, this term will give us the opposite sign to our first term when they actually should agree. This is a problem, but only a very small one because we can just stick a negative sign in front of our second term so that when we have an anti-clockwise swirl, this first term is positive and our modified second term is also positive. And just so you don't feel left in the dark, yes, when you have a clockwise swirl, both of these terms will be negative. Some small details. I explained the concept of curl by focusing on the center of a swirl, but curl also tells you the swirliness of a point even when it's not the center of a swirl. I guess I'll leave you to consider why our calculation still holds. I'm not going to animate everything, folks. Also, it is perfectly possible for the points of a vector field to have both divergence and curl at the same time. A nice example of this is a whirlpool. These properties do not interfere with each other or conflict in any way. You can even have a vector field that exhibits positive and negative divergence and positive and negative curl. In any case, we now have mathematical representations of the two very intuitive concepts of water being gained or drained from a point and water swirling around a point. And after all this talk about flow, you might ask, but what does this have to do with my interdimensional pizza delivery service? Well, my frustrated friend, we can now find out. See, these functions, whatever they may be, that represent the transformation between universes, have another representation. Initially, the way we represented these functions was by transforming the entire input plane using the functions and watching where the whole thing goes on an unaltered output plane. But let's leave the input plane unaltered, and instead of representing our input by putting it on the output plane, let's represent our output by putting it on the input plane in this particular way. If we pick a random point as our input, then maybe our transformed point as our output is over here. But we don't have to think about our input as a point. We can think about it as a vector where the size and direction of the arrow perfectly matches the size and direction of the gap between the center of the graph and the output point. This vector we will put on top of our input back on the unaltered plane. And for every point on our input plane, we will repeat this process of looking at the output, making a vector, and putting the vector on the input. So it turns out we have two ways of representing our transformation functions, and perhaps if we are looking for a special property in one representation, like the preservation of angles, there may be a special property in the other representation that corresponds. As in, say we already know our transformation preserves our pizza slices, what can we say about the related vector field? Let's take a very simple example. This transformation quite obviously preserves pizza slices, so let's look at its corresponding vector field. First, the vector at exactly the center of the graph is 0, as you can see, which makes things easy. But let's look at the point just above our original. Applying our transformation, we can see our input gets rotated and scaled by some amount to make our output vector. And before we try to make the vectors for other points, remember, we know this graph rotates and scales all inputs equally, which means we don't need to look at the output graph anymore as our reference. We know that whatever we did to this vector, we can do to these vectors too. All of these inputs will get the exact same transformation applied to them. What does this tell you about how water would flow around this point? It tells you that all of these vectors must be causing the exact same flow around this point. So it doesn't matter how you analyze the point, this way, this way, this way, or this way, from any perspective, a fish swimming through this point would always measure the divergence to be the same, regardless of the direction they went through the point, and always measure the curl to be the same, regardless of the direction they went through the point. This has a significant implication for our divergence and curl equations. Remember, our divergence equation was made from the divergence in the x direction and the divergence in the y direction. But now, we can say more than just what the divergence is. We can say that whatever the value of divergence is we get in the x direction, represented by this term, must be equal to the value of the divergence in the y direction, this term. And, applying the same logic to our curl equations, if from any direction our curl value is exactly the same, then our components of our curl equation must be equal. These equations holding true are the pivotal consequence of having a transformation that keeps your perfect pizza proportions. And just to verify this conclusion, if you consider what happens with the flow around a point that doesn't preserve angle, like this, you can see that the arrows are not doing the same thing around the point. And also, if you pick a point that doesn't have a zero vector at the center, it's a bit harder to imagine how these equations hold. Remember though, fundamentally we were looking at the difference between vectors, so we can slide everything on this graph like this, and all these calculations will give the same answers, so the equations will still hold. Our final understanding is this: that in order to know whether our pizza transformation preserves the angles of all our slices, we look at the equally valid vector flow representation, and if the flow around the point our pizza is perfectly spiral, then two things are true. Swimming through the point our pizza is at gets just as easy or just as hard in any direction, and the swirliness of the point is the same all the way around. Upon that being true, we know the components of our divergence and curl equations must be equal to each other. So, all we need to check is whether these mathematical statements are true, and we would know whether we can deliver our pizza. And so our problem is solved. And in case you wanted to know, these two equations are known as the Cauchy-Riemann equations. Normally they are written like this, since it's more abstract, but this is a little easier to appreciate. So, without a lick of partial differences or any reference to complex numbers, we now know that so long as our pizza's transformation implies the Cauchy-Riemann equations, we can safely deliver our pizza without risking a multiversal war. Or a refund. Wow, this has been an intense week. I only made this video to participate in the Summer of Maths Exposition competition, so I never anticipated doing a work like this. I normally do Lego stop motion videos, as you might have guessed, and if you're interested, there's a particular Bad Batch video I made on my channel. I'm quite proud of it. I've got a lot more animations on the way, they just take time. And in case you especially liked this video, I have to disappoint, because I've got no plans to do more maths videos. As I said, this was an exception for a competition. Also, I must admit that the video is kind of based on a lie. See, even when you don't preserve the angle, you know that all your pizza slices are going to have their area modified by the same amount, so you can still guarantee an equally shared pizza. It comes down to how you can locally linearize every point, and so you have a determinant at every point, and so an infinitesimal pizza will have all of its slices modified by the same amount. But, shh, let's pretend we never heard that. Anyway, if you want to know more about divergence and curl, I'd very strongly recommend Khan Academy's course on multivariable calculus. You'll get a much better understanding of the details and the application of the concept in this video. And with that, thank you for watching. This was great fun to make.